Gatekeeper Exposed.
Good morning. So let's talk about exposing Gatekeeper. My name is Patrick Wardle. I've worked at a bunch of acronymed places. Currently, I'm the director of R&D at SYNAC. So SYNAC does crowdsourced vulnerability discovery. In short, we think that currently humans are still better at finding vulnerabilities than machines. So basically, we have vetted security researchers, freelancers from all over the world who've signed up with us to find bugs in our customers' websites, mobile apps, IoT devices, and even networks. I'm going to let you know a little not-so-secret secret. Our customer security really sucks, so we end up paying out a ton of money to our researchers. One of our top researchers is about to hit $200,000 that we've paid out for vulnerabilities. So if you're interested in doing some bug bounty hunting, finding some vulnerabilities, some web apps, and getting paid, definitely check out synac.com. All right, so today's talk is going to be divided into three parts. We're going to start with a brief technical overview of Gatekeeper. Following that, I'm going to talk about ways I found to bypass Gatekeeper. And then finally, we're going to end with how I wrote a tool to protect Mac users because, as we'll see, Apple screwed up some patches. Now, before attacking any technology to look for security vulnerabilities, I think it's good to thoroughly understand it. So let's dive in and talk about how Gatekeeper works under the hood. Now, I'm sure you're all aware, you're security professionals, that yes, contrary to what Apple kind of wants us to think, Macs do in fact get malware. Turns out, though, most are Trojans, which means they require user interaction to achieve infection. So since about 2006, we've seen a good number of OS X or OS X Trojans and many, many Mac users infecting themselves. So in 2012, Apple had been kind of getting tired of this. Basically, there's all this news about Mac malware and all these Mac botnets. So they decided to do something about this and introduced Gatekeeper. So Gatekeeper is a built-in security component of OS X, and it has really one job, one goal. And that is to block unauthorized code from the internet in order to protect naive Mac users. So Apple states that if a downloaded application was developed by an unknown developer, that's one with no developer ID, or was tampered with, for example, in download, Gatekeeper can block the application from being installed. Now, as you can see on the slide in the pop-up there at the bottom, if the user even tries to run this unauthorized or tampered code, Gatekeeper will detect and throw up this pop-up, and the only option is to click OK, which essentially kills the application. So the user can't run the application easily, even if they try to. Now, Apple touts Gatekeeper as an essential core OS component, and one could argue that it's one of the cornerstone technologies kind of their security posture. So there's two scenarios where Gatekeeper can protect Mac users. The first is it can help prevent users who are tricked into downloading and executing malicious code. And honestly, attackers are pretty convincing, so you can't blame users too much, right? We're probably not going to fall for these attacks, but there's a decent percentage of the population that's going to be tricked into these attack scenarios, right? There's this quote I like that's basically, there's no patch for human stupidity. So Gatekeeper does a pretty good job blocking attacks from a variety of sources. For example, if a user goes to a website and it's been hacked, or if it's a malicious website, it might try to trick the user and say, hey, your computer is infected. Please download and install this application to clean your computer. And of course, when the user downloads and runs that application, then they're really infected. Or similarly, if users go to an adult website that's malicious or been hacked, it might say, hey, in order to watch the adult content, please install this plugin. So I've been told. Obviously, if the user goes and installs that plugin or that code, it's going to be malicious, and then they've just infected themselves. So Gatekeeper, again, tries to protect naive users, even if they are tricked or coerced into running something that's potentially malicious. Now, Gatekeeper can also protect OS X users from more advanced adversaries. If content is distributed insecurely, so for example, over HTTP outside the Mac App Store, an attacker with network-level access may intercept and inject malicious code into the download. Luckily, Gatekeeper verifies the digital signature of any download, so we don't, in theory, have to worry about it. And since it's 2016, you would think that most downloads are distributed over HTTPS securely anyways. Well, it turns out, unfortunately, that's not really the case. I looked at some security products last year, and actually every single piece of Mac security software was distributed legitimately from the company's websites over HTTP. So again, this means if there's a network-level adversary, maybe a nation state or someone with such capabilities, they could, in theory, man in the middle of this attack. So this is kind of unfortunate. But luckily, in theory, Gatekeeper protects us against this. All right, so how does Gatekeeper actually work? Well, at a pretty high level, it's actually fairly straightforward. So when a user downloads a file, a special quarantine attribute gets added to the file. Then, when the user goes to run this downloaded file, for example, by double-clicking, since the quarantine attribute has been set, Gatekeeper checks the file to ensure that it conforms to the user's Gatekeeper settings. So the default is to only allow apps that have been signed, either with an Apple Developer ID or by Apple proper. But you can jack this setting up to the very most stringent level, which will only allow code from the Mac App Store. So let's take a closer look at this quarantine attribute, because this is what triggers Gatekeeper inspection. So in OS X, files can have extended attributes, basically file metadata. For example, when you color a folder in Finder, it's stored as an extended attribute. And yes, the files that are downloaded from the internet get tagged with a quarantine attribute named com.apple.quarantine. Now, you can view these from the terminal via the xadder command. So here you can see I've downloaded a text file using Chrome, and if I use the xadder command, I can dump some of the extended attributes. And for example, we can then see that com.apple.quarantine attribute. So the com.apple.quarantine attribute was originally just used for a technology called file quarantine. This was introduced in Leopard, and it's still used today. And it's responsible for the pop-up you get for any downloaded content from the internet that says, are you sure you want to open this file because it was downloaded from the internet? Now, it's very important to understand that first, this is not Gatekeeper, this is file quarantine, and also this pop-up is going to be shown for any content. Even content that's signed, has not been tampered in transit. It's just an extra layer that Apple kind of likes to put up there. Today, this attribute, as I mentioned, is also used as a kind of like a trigger event for Gatekeeper. Now, besides using the xadder command, you can also programmatically dump the extended attributes for any file. So here I've done it programmatically. It's just a dictionary, and it's serialized, so it's very easy to dump. And if you do it programmatically, it kind of parses out a little better. So again, for the text file I downloaded, we can see there's the application that downloaded it, a timestamp when it was downloaded, and the URL from where the file was downloaded from. Now, I've said a few times that this quarantine attribute is added for all files that are downloaded from the internet. Well, it turns out this is kind of an oversimplification. So here I've coded up a custom downloader. It's a few lines of code, just a little UI app. User puts in a URL, clicks download, and it will download the file. If we then run xadder on the file that was downloaded, we can see that there are no file attributes, which is kind of weird because this file was just downloaded from the internet. So what's going on? Well, it turns out it's the responsibility of the downloading application to support the notion of quarantine attributes. So there's two ways an application can support this. The first is manually. So an application can call the setResourceValues method and pass it a dictionary, just a key value pair. And the key should be NSURL quarantine properties key. And then the values are any values you want for the quarantine attribute. So here I've re-extended the code in my custom downloader, and now any file that's downloaded with my little app will have the quarantine attribute set. Now, doing that manually is a little tedious. You got to add some extra code, so kind of problematic. So Apple decided to make it a little easier. So it turns out that you can simply set a key in the application's info.plist file, which is just an XML property list file. And basically, if you set the ls file quarantine enabled key and set it to true, now anytime a file is downloaded via this application, the operating system will automatically add the file quarantine attribute for you. So your application still has to set this value in the property info.plist, but other than that, every file will automatically have that quarantine attribute. So here again, I took out my old code, just set that property list key, and now any file that's downloaded, you can see has that quarantine attribute set. All right, so that was the quarantine attribute. Again, anytime a file is executed that has this set, Gatekeeper will automatically be invoked and will examine the file. So the end-to-end Gatekeeper process is, somewhat rather complicated, as this overview shows. There's lots of different steps, user mode components, kernel mode components, and whatnot. But no worries, we're kind of going to dive into each of these steps so we have a really good understanding of exactly what's going on. So the first thing is a user double-clicks a file that they've just downloaded. And in this case, we'll assume the file is unsigned, so eventually Gatekeeper will actually block this. So Finder will handle this click, and by means of the launch services framework, we'll send an XPC message to get the application launched. An XPC message is simply an IPC message. It's a message that's sent to another process. So specifically, as the call stack shows, the spawn via launchd function is invoked to send the message. And I've dumped some of the arguments, some of the values that are in this message, and we can see there's a label, the path to the application, and then this interesting attribute that is spawn via launchd stopped flag. And what this does is this indicates that that application should be launched but in a suspended state. And we'll see that this is what allows Gatekeeper to validate the application, and if it's unsigned or not trusted, it'll kill it. So the application will be spawned, but it'll be in the suspended state. Nothing will have actually run yet. All right, so launchd gets this XPC message from Finder. What it does is it simply turns around and makes a system call, POSIX spawn. Now, if you look at the call stack, now this is in kernel mode, so the kernel call stack, you can see that this call passes through Apple's quarantine.kext. It's a kernel extension. Specifically, it calls the hook vnode check exec function. Now, this function is part of a policy module for mandatory access control, or MAC. Now, unfortunately, I don't have time to kind of dig into all this kernel policy, but suffice to say, it checks a few flags, and then will bail early if the user has previously approved this file, or if this file is on a read-only file system, for example, a DMG that was downloaded from the internet. All right, so now we're back in user mode. The application has been spawned, but is in a suspended state, so nothing's actually running yet. Now, if the app has the quarantine attribute set, Launch Services makes another XPC request, this time to Core Services agent, Core Services UI agent. Again, you can see I've dumped the arguments in this message, and we can see, again, it includes the application's path and then some interesting parameters such as a risk category. So as its name implies, the Core Services UI agent is a core service that can handle UI, so pop-ups and whatnot. Again, if we look at the stack trace, we can see that when it gets an XPC message, it utilizes a class called GK Quarantine Resolver to talk to the XProtect framework. Now, this framework gets the file's signing information via a call to the seccopy signing information, and then classifies the file even if it's not malware. So this is actually kind of where Gatekeeper proper is really doing its thing. It's examining the signature of the file, verifying it to make sure it's not tampered with, and then we'll classify that file. So once the XProtect framework has processed and classified the file, Core Services UI agent creates an alert. Because remember, in this case, the file we just downloaded and are trying to execute is unsigned. So you can see the GK Quarantine Resolver alert for path method allocating an NS alert. And an NS alert is just how you create a pop-up in OS X. So at the bottom right, you can see the snippet, some disassembly that handles what happens when the user clicks OK. Because again, this file is unsigned, there's no option to even allow the user to run it. It's just going to tell the user, I'm blocking it. And when the user clicks OK, as we can see in the disassembly, it actually kills the unsigned or the unapproved applications, specifically by calling lskill application. So this is how Gatekeeper actually blocks the application from actually running. All right, what happens if the downloading application, though, was signed and approved by the user? Well, two things. First, the quarantine attribute flags get updated. Specifically, they get OR'd with OX40. And then, remember, the application was spawned in a suspended state. The OS will then call lssetApplicationInformation item to resume the application. Because at this point, Gatekeeper has said, hey, this app looks good. Yes, it's from the internet, but it's signed. I'm going to allow it. So I'm going to allow the application to resume, and then the application can execute and do its thing. So that's a fairly technical overview of file quarantine and Gatekeeper. So now let's talk about how we can get unsigned, unauthorized malicious code to execute. Now first, I want to reiterate the goal of Gatekeeper, and that is to block unsigned, unauthorized code from being able to execute even if the user tries to run that. So our goal then is to get unsigned malicious code to run. Now I first want to talk about some known shortcomings of Gatekeeper. In my opinion, these are not bypasses per se, they're just good things to be aware of. So first, if you have a remote exploit, for example, in Flash or in a browser, if your shellcode is able to download a file, it can likely ensure that that file doesn't have the quarantine attributes set. You know, it can manually remove them or manually download it to make sure that quarantine value isn't even there. I've added a quote to the slide that articulates this. But again, if you have remote arbitrary code execution, you're not going to have to be worried about Gatekeeper. Because again, Gatekeeper only gets invoked if the quarantine attributes are set on the file. As I showed earlier, the downloading application also has to support the notion of quarantine file attributes. Luckily, essentially all major applications today do. So browsers, email clients, chat clients, they all will, for any file downloaded from them, will have this quarantine attribute set. However, there's some smaller or third-party applications that don't support the notion of file quarantine attributes. So one example of this was iWorm. iWorm was a Mac Trojan, wasn't a worm, rather just a Trojan, that was spread via infected applications on Pirate Bay. So Photoshop, those kind of things, right? So users would be enticed by that, they would download that and run that. So even though these applications were unsigned and malicious, the torrent downloader, for example, muTorrent, did not support file quarantine attributes. So the file would never get that quarantine attribute set. So when the user double-clicked to run it, Gatekeeper would never get invoked, never examine the file. And yes, users would get Photoshop, but they would also get iWorm installed on their computer. Now, there have also been a few generic Gatekeeper bypasses. The first is CVE 2014-8826, and it leveraged a malicious jar file to bypass Gatekeeper. However, it required Java to be installed. Now, the two I'm going to be talking about today worked on any default OS install. The first was an attack I described last year that leveraged dilib hijacking to fully bypass Gatekeeper. And then the other one I'm going to talk about today as well was a newer attack that also affected El Capitan. All right, so the first bypass I found. Now, I examined Gatekeeper, and I found that it does a great job verifying the downloaded application bundle that gets executed when the user double-clicks this. If you touch this at all, it will break the digital signature, and then Gatekeeper will resoundingly block it. So you really can't modify that application bundle at all. But external content was not verified, which is generally okay unless the application that the user runs is linked against such external content. So what we can do in three steps is pretty easy to bypass Gatekeeper. So the first and most important is we need to find a signed application that contains an external relative dependency to a hijackable dilib. We'll show what this means in a second. And then what we can do is we can build a malicious installer package, a DMG image, a zip image, that we can create the necessary folder structure. And then we can either host this online and try to coerce users into running it or downloading it, or more stealthily, we can now inject this into insecure downloads if we have network-level capabilities. All right, step one, and this is the most important one. We need to find a Gatekeeper-approved application with a relatively external dependency on a hijackable dynamic library. So it turns out that instruments.app fits the bill. We can see that it's trusted, it's accepted by Gatekeeper, right? It's signed by Apple proper, so this means if the user downloads instruments.app, it's always going to be allowed to run. However, if we dump its dependencies, its imports, the libraries that it imports to run, we can see that one exists outside the application bundle, outside the application packet, but relative to. So this means we can put this all in the same installer package. Now, the reason instruments.app has this is it doesn't really expect to be distributed independently. It's installed under Xcode, which is Apple's IDE, so it makes sense for it to kind of have some shared dependencies on that, some code reuse. But basically, when instruments.app is run, the OS loader will look at its dependencies and take wherever directory instruments.app is, go up, in this case, 1 or 2 directories, and look for that dilib and then just load it. So now we can create an installer package with that required setup, basically. So as I mentioned, the hijacker dilib is external. Specifically, it's in the shared frameworks directory. So we can create this file structure, this folder structure, directory structure, on a DMG, on an installer package. So at the very top, you can see in the applications directory is instruments.app. And then we have the other folders, for example, the shared frameworks directory. And there we put our malicious unsigned dilib. Now, if the user sees this in an installer package, they're going to be confused. They're like, what do I click? What are all these extra files? So obviously, we should clean this up a little bit. So we can hide the files and folders that we don't want the user to see. We can set a top-level alias, so there's one nice thing for the user to click on. And we can change the icon, background, and make it read-only. So if we do this, this is an example of a DMG image that we can present to the user. Now, this is great because we can fully customize it. So in this case, say the user has been tricked into downloading a fake Flash update. We can build this DMG so it looks exactly like this. Or if they are even downloading a legitimate Flash installer that's distributed over HTTP, again, this is the DMG we can provide to them. It's pretty convincing, right? So what happens when they run it? Well, first we have max gatekeeper settings. So it's jacked up all the way to say only allow code from the Mac App Store. Once the user gets this DMG, either they are tricked into downloading it or we inject it into an insecure download. Once they click on it, they will get the quarantine pop-up. But again, this happens for any file that's downloaded from the internet, even if it's signed and been untampered with. So they're likely going to click OK because they are in the process of downloading software. So once they do it, Gatekeeper will examine what is being executed. And it's really instruments.app. So Gatekeeper says, all right, this is validated, it's signed by Apple proper, I'm going to allow it to run. And as soon as it lets it run, the OS dynamic linker and loader will start loading the dilibs that instruments.app is dependent on. Remember, one is external to the application directory, is not validated, so we'll load and execute this. As soon as it executes this, we have unsigned code execution, and we can kill instruments.app before it's even shown to the user, because remember, in this case, they're probably expecting a Flash installer. And then we can obviously show the user whatever they want. So we can kick off a legitimate Flash installer while in the background installing some malicious unsigned malware. All right, so Apple patched this, and I'm going to talk a little bit more about the details of how they patched it, but they basically statically check the downloaded application to make sure it doesn't have any of these external dilibs. But external content is still not verified, which is a problem if the application either executes or dynamically loads at runtime any other external content. So here's another gatekeeper bypass. So again, step one, the most important, you want to find a signed application, something that's going to be accepted, verified by Gatekeeper, that at runtime loads or executes a relatively external binary or dynamic library. And then again, you can create this malicious installer package that can be hosted online or injected into an HTTP download. So first example is Photoshop. When Photoshop executes, as the pseudocode on the right shows, what it does is it looks up one directory from its application bundle for a folder or directory called plugins. And then it iterates through all of that, and any plugins it finds in there, it loads them and executes it. Now this is all done at runtime. So Gatekeeper has already validated Photoshop.app. It says, okay, it's valid, it's signed by Adobe, it has not been tampered with, looks good, and then lets it run. And then, again, these malicious plugins get loaded. So this is, again, how we can bypass Gatekeeper. Now, there's some limitations of the Photoshop attack. One, it requires Photoshop to be run. So this is great if you're tricking users into downloading a free version of Photoshop. But if they're trying to download, say, some Mac security software, and you inject Photoshop into the download, it's going to be massive. And then when they double-click what they think is the the AV installer, Photoshop's going to pop up because it has to run before the plugins get loaded. So it's really not that stealthy. So I wanted to find kind of a better attack that would work on any Gatekeeper settings and also would be a lot more stealthy. So what I did was I found an Apple signed binary called ICTool that, when executed, looks for an executable called IBToolD in the same directory and then executes it. So since the second tool, IBToolD, is programmatically executed, it is not verified by Gatekeeper. So it can be unsigned or malicious. So again, here's the full attack that can be delivered as a malicious installer package, hosted online, injected into an HTTP download. So the first thing I do is I create a top-level alias that points to Apple's tool. This is ICTool. And again, you can name the icon, place whatever icon you want, change the name of this, whatever. And this alias now ensures that when the user clicks it, the Apple sign tool will be run. So that Apple sign tool, ICTool, again, you can rename it to whatever you want. It's important to add the .app extension because it's a command line executable. And on Mac OS X, when you double-click on a command line executable, terminal window pops up. If you rename it .app, that does not happen. So that's good because we don't want terminal windows popping up on the user's desktop. So then what you do, step 3, is you plant the binary that matches what Apple's binary is looking for. So this is IBToolD. Again, this can be unsigned, malicious, whatever you want it to be. And then step 4, if you need to turn around and execute another application, since ICTool and IBToolD are both expected to be command line tools, your unsigned IBToolD can obviously execute anything at once, including a nice application for the user to see. So Gatekeeper was trivially broken, in my humble opinion. I thought it was, easy to bypass, completely broken. So let's talk about what Apple did to fix these vulnerabilities. So Apple patched the first bug in Yosemite Service Pack 4, and the second bug in El Capitan Service Pack 1. So let's look at exactly how they went about patching these vulnerabilities. The first one, recall, is when an application is statically linked against an external dynamic library that can be placed within the same malicious installer package. So when Apple indicated that they had released a patch, I reran my proof of concept, and it failed, which was a good thing from a security point of view. And it gave me a nice error message in syslog that basically said, fails dilib check. So it appeared that Apple had now implemented a patch to verify externally linked external dilibs. So I grepped the file system for that string, for that error message, and I found it within the xprotect framework, which makes sense because this is pretty much where Gatekeeper proper is implemented in user mode. So I disassembled the xprotect framework library, and you can see that there's a new method there that was implementing that's called perform dilib bundle check. And as you can see in the disassembly, if this method fails, the error message is then displayed in syslog. So this is kind of where the patch is actually being implemented. If you do some dynamic debugging, you can determine the arguments that are passed to this new method, the patch method. We can see basically arg0 is the class, arg1 is the method name, and then the final arg3 is actually the path to the application that's about to be executed. Again, this makes total sense. Gatekeeper is verifying what's being executed, so it makes sense that this function would take a path to that application. So I reverse engineered the perform dilib bundle check method, and I found that it does three things. First, it allocates an instance of a new class called xprotect dilib check. You can dump the methods for this new class using something like class dump. Once an instance of this class has been instantiated, it invokes the parse mock-o method to actually parse the executable. And then finally calls check commands with bundle URL. So check commands with bundle URL method is really the heart of this new patch. So let's reverse engineer to find out exactly what it does. So it turns out it does two simple things. So for all dynamic library dependencies, anything that's statically linked in the application that's about to be run, it ensures two things. It ensures that either these dynamic libraries exist within a trusted system directory, so something like /system or /library, or that they fall within the application's bundle. So in short, applications that are linked against dilibs, even signed dynamic libraries, that are outside the application bundles, but not in an allowed trusted OS path, are going to be blocked. This is actually a fairly reasonable patch, but it only patches this one very specific attack vector, right? External content is still not really verified. All right, so on to the patch for my second bug. Again, I started by rerunning my proof of concept, and again it failed, which from a security point of view is a good thing. And again, it gave me this nice error message in syslog, specifically failed gatekeeper check, or failed GK check. It's kind of a helpful thing. So again, I grepped the file system. I actually started at looking at xprotect framework again, because that's where the first patch was implemented. And yes, that string showed up in that same binary. So I disassembled that file again, looked for a cross-reference to that string, and again, I found a new method. This one was called perform block list check. Now, I dynamically debugged this method to see exactly what was going on, and I found it takes a path to the application that's about to be run, which again makes sense, and then a list of something called block sigs, which I thought was interesting. So then I reversed the perform block list check method and found that it does two simple things. The first thing it does is it gets the application ID of the application that's about to execute. So again, this is the application that the user has downloaded that Gatekeeper is in the process of verifying. And then it checks if the application ID is in a hard-coded blacklist. So basically all Apple did in this patch was blacklist the applications that I had abused in my proof of concept. Sorry, Apple. So let's summarize Apple's patches. The first one seems likely to prevent these external statically linked dilibs from being abused. But again, it only specifically blocks that one attack avenue. The second one just blacklists the very specific binaries I abused in Apple's in my proof of concept that I provided to them. So again, neither generically blocks the execution of unsigned internet code, which is what Gatekeeper claims and seeks to provide. Now, since Apple's patch for the second bug, CVE 2015-7024, was so, in their words, targeted, it's conceptually trivial to bypass. So all we need is three things. First, an Apple signed binary, which means a binary that Gatekeeper will always approve or allow. that calls execv or posexpon or system, so in other words, execs another piece of content, on a relative binary, so one that can be placed in the same installer package. And I do want to point out that when I talked to Apple about this originally and provided them with the proof of concept, I articulated this very clearly. I said, guys, there's a systemic issue that Gatekeeper is not validating external content. Here's a proof of concept illustrating this, but there's probably lots more applications out there. I'm really kind of lazy, so I found a few, that should illustrate the problem, but, there's going to be more. So I wrote a simple script that looked for Apple signed binaries that called execv on relative binaries. And I kicked this off, went to lunch. Came back, and it found a list of candidate binaries, and it turns out the first one it found was a winner. Well, how so? If we monitor the file I/O for ACTool, which was the first binary I found, we can see that when it's executed, it looks for a binary in the same directory called IBtoold. And then at the bottom, you can see if we place a binary in that same directory called IBtoold, ACTool, if it finds it, will execute it. So perfect. This is exactly what we need for our attack. So literally, all we have to do to bypass Apple's patch is take the same original proof of concept and simply replace ICTool, which was blacklisted, with ACTool. Right? And this allows us to bypass Gatekeeper even on, at the time, a fully patched OS X system. Again, I'm sure there's lots of other binaries that could be abused. So, again, I'm lazy. I found one, kind of good enough. Game over. Proves the point. All right, so video time. I just want to kind of illustrate this attack visually. And a few observations. First, this is a OS X 10.11.2 box, fully patched. Gatekeeper is enabled. And then there's only 4 launch items that are running, and there's no process called Java W. All right, so what we're going to do is we're going to man in the middle Kaspersky download. Because, as we'll see, Kaspersky distributes their Mac security software over HTTP. No idea why. So the user goes to Google. They've like, oh, I heard Patrick talking. There's Mac malware. I should protect themselves. So they type Kaspersky Internet Security. This is Kaspersky's website. I haven't man in the middle of this, but when they click the download button, this is going to start an HTTP download. Now, what I can do is intercept that download and inject malicious unsigned code. So what I'm going to do is inject a copy of iWorm, which is known and unsigned. So in theory, Gatekeeper should block this, 1, because the download has been tampered, and then 2, it's been tampered with unsigned malicious code. So, you would hope that Gatekeeper would protect the user from this. So as soon as the download finishes, the user's going to double click it because they're running software. It's going to get the quarantine pop-up that basically just says, hey, you downloaded Kaspersky. Again, this pop-up would be there even if this Kaspersky download was not tampered with. They get the download, the DMG, they double click on it, and we can see in a second the Kaspersky installer pops up. So for the user's point of view, nothing weird has happened. Gatekeeper hasn't popped up and blocked the executable. There's nothing weird going on. But if we look at the process list, we now see there's a new process called Java W running. And if we look at the code signature for this, and you can do that with the code sign -d_vdd flags, this will examine the code signature status of a file, we can see that it's unsigned. So basically there's a new process running that's unsigned. Again, Gatekeeper is supposed to block these things. Also, if we go to knock knock, we can see that there is a new launch agent that's been installed. Specifically something called Java W. So not only was the unsigned code able to run, it was also able to persist itself. And if we look at this file a little closely, we can see that VirusTotal has flagged this, and if we load up the VirusTotal page, we can see that this is, again, iWorm known piece of malware. So again, this is a complete fail on multiple levels, right? Gatekeeper is supposed to block tampered downloads, and it's supposed to protect against unsigned malicious code running. Again, this was on a fully patched system, and again, this is kind of the attack scenario that keeps me up at night, where I'm sure there's adversaries out there that are able to download or intercept man-in-the-middle insecure connections. So now they have a capability to attack even fully patched Mac OS X users. All right, so Apple did actually blacklist ACTool a few days ago. So again, they were like, well, we should do something about this. Let's just blacklist the new binary that Patrick found. Again, there's tons more. So obviously, they didn't fix the systemic issue. Since Apple has, again, kind of showed that, I'm going to choose my words carefully, somewhat of an incompetence from a security point of view, let's look at how we can kind of take matters into our own hands until they release a real fix. And they have indicated that they are working on a more comprehensive fix. It's just taking them some time. So first I looked into seeing if I could use various OS level code signing enforcements. And you can do this via syscontrol. It turns out there's a flag called VM-CS enforcement. It's undocumented, but it seems to enforce globally code signing on all processes and libraries. However, when I enabled this, even in a clean VM, I got a lot of crashes. So like Safari would just randomly crash. And it's also global. So this means like everything has to be signed. So I develop a lot of software, which is annoying if I can't debug it if it's not signed. So in my opinion, this is really not a good option. It's undocumented, it seems to break even Apple software, and it's global. So in my opinion, I think we need a custom fix, a custom solution. Now, after I detailed the first gatekeeper bypass using dilib hijacking, Pedro, also known as OS X Reverser on Twitter, released a neat tool called GATEKEEPER. Basically, it's a kernel extension that installed a mandatory access hook on mmap. And what it did was it blocked unsigned pages in any signed process. Now, this is great because it thwarts dilib hijack attack, but it doesn't prevent the second bug class, the standalone binaries. But I really like this tool. He open sourced it, and it really inspired me to write another tool. So I figured I'd write a similar tool that simply blocks the execution of all unsigned binaries from the internet. If that statement sounds familiar, it's because that's what Gatekeeper says it'll do. So it turns out Apple actually already uses sandboxing to validate a lot of things at runtime. And I figured it'd be trivial to create a runtime hook to monitor execution without a performance hit. So conceptually, what we're going to do is three things. We're going to check anytime a new process is started, does that binary have a quarantine attribute, meaning is it from the internet? And then we're going to check if it was previously approved by the user. And if it wasn't, we're going to make sure that that binary is signed. So in other words, we're going to block unsigned, non-approved internet binaries. Again, doing what Gatekeeper says it will do. So the first thing we need to be able to do is monitor process creations. So we can check if a binary is from the internet, and if so, if it's signed and trusted. Now, I wrote a series of blog posts on this that detail how to do this. But in short, we can use the kernel authorization, or KAuth subsystem, to do this. And Apple provides this framework for kernel developers, and it's actually a really nice framework. Because what you can do is you can register a listener for a whole variety of events, such as process creation. And then the OS will automatically call you anytime that event occurs without really incurring much of a performance hit. So this is what the code looks like. We first invoke KAuth listen scope. This basically tells the KAuth framework, hey, we're interested in some event. And you pass a scope. There's a variety of scopes. We choose the KAuth scope file op scope. And then we also provide a callback. And since we registered the KAuth scope file op scope, anytime a file event occurs, we will get automatically invoked by the operating system. We can see what we do is we ignore all file operations except for file exec. And this means, or will indicate, that a new process is being created. So how do we determine if a process's binary is from the internet? Well, again, recall quarantine attributes. They're added to basically everything that's downloaded from the internet. So I reversed Apple's quarantine.kext file to see how they did it. And they call this undocumented function mac vnop get xadder. Basically, you pass a vnode to the file, so the process that's about to be spawned, and then a string, in this case com.apple.quarantine attributes, and it'll fill a buffer with the value of that quarantine attribute. So now we have a way to get quarantine attributes for the process that's about to be executed. Turns out, though, it's not quite that easy. So when you double-click a DMG image to mount it, while the DMG image, if it's from the internet, will have the quarantine attribute, the files themselves will not. So when the user then goes to double-click a file that was mounted, and we look at that file actually doesn't have any quarantine attributes, even though that file is essentially from the internet, right? It came in a DMG from the internet. So this means that files executed off the DMG don't have quarantine attributes. So what can we do? Well, it turns out we can map the file back to its DMG and then check that DMG to see if it has file attributes. It's a touch complex, but basically we can do this in 5 steps. So the first thing is we check if the binary is running out of /volumes, which indicates that it's on a mounted file system. We then get a mount structure for the binary's vnode, and then we get a statfs structure. And we can extract the f_mount from name value, which will have a BSD mount path, so something like /dev disk1. We then iterate over the IO registry, which is kind of a tree of all devices that the kernel keeps. And we're looking for a parent that has a child with that same matching point. So again, we're looking for a child that has something like /dev/disk1. If we find a child that has that same BSD mount point, the parent actually has a member called image_path, which has the full path to the DMG. Now we have the DMG image, we can access the file quarantine attributes to see if it was from the internet, and therefore know that the file that's being executed, even though it does not have the quarantine attributes, came from the internet by means of this DMG image that was mounted. All right, so recall we want to block all downloaded binaries that aren't signed. So via the quarantine attributes, we can determine if something's from the internet. However, we don't want to block files that were explicitly or previously approved by the user. Again, reverse engineering Apple's quarantine.kext, we can see they check the quarantine attributes for a flag with a value of OX40. Rather, they order that out to see if that bit is set. And recall in user mode, this is what was set when the user clicked OK to allow a file. So we basically just check for that flag value, and if it's set, this means that the file was previously approved by the user, so we're going to allow it to run. So if we get to this point, we have a downloaded binary that was not previously pre-approved by the user. So all we have to do now is check if it's signed. Turns out this is actually kind of hard to do from user mode because there's no public or exported API methods you can call to check if a file or an executable is signed. If you reverse engineer or actually look at some of the source code for Apple kernel, you can see that they do this though. Basically, they lock the vnode for the file and then get a pointer to what they call a UBC info structure. And then in this structure, they check for a pointer to a CS_blob structure. If this CS_blob structure is null, it means the file is unsigned. If it's not null, it means it is signed. Problem is, Apple's code uses a lot of unexported functions and undocumented structures. But that's not going to stop us. So if we reverse engineer the vnode lock function, which is not exported, we can see that it just calls lock mutex lock, which is actually exported. So we can just call that directly. Then it turns out the offsets for these various private structures are all the same in all versions of OS X 10.11. So we had some versioning checks to make sure our kernel extension is only going to run on that operating system, but then we're good to go because the offsets are all the same. So here's the code which allows us to determine if a binary is signed or not from kernel mode. All right, so putting that all together, I created a tool that can provide some protection. It's called Ostiarius, which is the Latin word for gatekeeper. The tool was released on my personal OS X security website, and the kernel component is signed, meaning you don't have to do anything crazy like turn off code signing. It's open source, and it generically protects against runtime attacks. I have it running on my laptop, and I will continue to run it until Apple gets their act together. All right, so let's wrap this all up with some conclusions. First, I just want to reiterate, Apple wants us to think that Macs, never get malware, never get infected, and just in case they could, there's this great product called Gatekeeper that protects Mac users from both Trojans and man-in-the-middle downloads. But unfortunately, the reality is Gatekeeper only currently protects Mac users against very lame attackers. And Apple has some issues about patching things correctly. And I think this is bad for a variety of ways. One, it really gives users a false sense of security. Right? When you report a bug to an operating system vendor and they release a patch, I personally and a lot of people trust that that patch is valid, right? Most of us aren't going to go out and revalidate the patch because it's a lot of work, right? We've already reported them a bug for free. They don't have a bug bounty program yet. So we're kind of doing them a big favor. So when they patch it, we assume that it's patched. The problem is Apple has definitely messed up some security patches recently. I gave a talk at DEF CON about how they messed up the patch for RootPipe, which was a nice privilege escalation vulnerability. Again, I was able to trivially get around this and re-exploit the vulnerability even on a fully patched system. So if I'm an evil Mac hacker, all I'm going to do is wait till Apple releases a patch. I'm going to reverse engineer it to find out what the bug is. Yes, I'll be able then to target unpatched users, but if Apple is screwing up all these patches, well, you've basically just got a free 0-day, and now you can target even users of fully patched system. So I'd rather Apple take a little more time and then patch things validly, fundamentally, and really address the issue as opposed to just putting a bandage on it. Now, I know I knock Apple a lot, but I've definitely drank the Apple juice. I'm an avid Mac user. I love Apple. I'm not sure they love me, but I'm okay with that. And I've done a decent amount of OS X reversing, and I keep finding these trivial bugs and these past bypasses. And obviously, if I can find that, yes, I have a lot of experience, but obviously there's going to be other hackers out there, nation states, reverse engineers, that might be a little more evil. So that bothers me. I really don't want my Mac computer to get hacked. So I figured I should write some OS X security tools for myself, first and foremost, selfishly, but then I should make them available for free so that other Mac users can possibly be protected as well. So my side hobby is to run a small OS X security website. It's got a nice collection of recent OS X malware. The AV community doesn't really like to share their samples with random security researchers, so I spent some time kind of getting a nice collection together. So if you want to reverse engineer some Mac malware or see kind of how it works, there's a nice collection. Then I also have these tools I wrote that protect my Mac that I share for free. So the first tool, Task Explorer, it's pretty much like Process Explorer on Windows. Shows all running processes, loaded dilibs, but you can do cool things like, say, show me all unsigned components that are running. So either unsigned processes or unsigned dilibs. It's integrated with VirusTotal. You can say, show me anything that's flagged or anything that's not from Apple. So it's a really good way to kind of figure out what's going on in your computer. Knock Knock we saw in the video. It's basically just auto runs for OS X. Again, shows you what's persistently installed on your Mac computer. Again, integrated with VirusTotal, so you can see if you have any malware or just maybe why your computer is running slow. Block is very complementary to Knock Knock. It monitors the persistence locations that Knock Knock examines. So it's almost like a firewall for these locations. It provides real-time monitoring capabilities, and anytime anything goes to persist software on your Mac, you get a pop-up saying, alert or deny. And since I released it last year, all publicly available Mac malware samples that came out after the fact, Block would detect and warn the user. Because again, all these Mac malware samples tried to persist. Kex Viewer is a simple utility to show kernel extensions, integrated again with VirusTotal. Talked about BINARIES today, and then the dilib hijack scanner will detect if you have any dilib hijacks on your computer or if there's any applications that are vulnerable. All right, so that's a wrap. I will post the slides on Twitter, and we have 3 minutes for any questions. So I'm just going to ask one question because there's a prize for the first question.
Where do babies come from?
Ask Apple. You do.
Would you recommend using any kind of third-party antivirus software on a Mac? Especially if it comes on over HTTP?
So Apple actually has a built-in antivirus product, XProtect, that it's based on static signatures, which is weak but will protect you from known issues. So unknown stuff is probably not going to get detected anyways. I do run Little Snitch, but stay tuned for that.
All right, thanks.
You're welcome. Any other questions? All right, well, thank you again. I know this is one of the last talks of the conference, so I really appreciate you all staying. And I also want to thank Apple for continuing to give me materials for talks.